Okay, I wanted to go through some more of looking at the domain of composite functions. So what I've got is a polynomial, a square root function, a reciprocal function, and an absolute value function. And what we're going to do is we're going to look at the domain of the individual functions and then the different composite functions that you can come up with. So this is a polynomial, so the domain is all real numbers. The square root function, x has to be greater than or equal to -2. If it's less than -2, then you get a negative square root of a negative number. It's not allowable. Here, you just have it that the denominator cannot go to 0, so it's all real numbers except x cannot equal 3. That'll make the denominator go to 0. And here we have the absolute value function, which is good for all real numbers. So those are the domains of the individual functions. So let's look at these different composite functions. So if we do f of g of x, what that's going to be is equal to the square root of x plus 2 quantity squared plus the square root of x plus 2. So all I've done is substitute this into here. Now, I haven't simplified it, and that really is where you need to look at the domain. What is the unsimplified domain? Now, in this case, the simplified domain is the same, but if you had just x squared, if you square this, you'd end up with x plus 2, which would be a polynomial, but that would be incorrect. You have to look at the domain in its unsimplified version. So for you to be able to evaluate the square root of a number, the argument has to be greater than 0. So the domain for this composite function turns out to be the same as the domain for the square root function. Okay, let's look at the other way. G of f of x. So then we're substituting this into here. So you'd end up with the square root of x squared plus x. I'm substituting it for x plus 2. Now here you can see that I haven't simplified anything. And are there any cases where this result would be negative? So the domain would be such that if this argument were negative, then that's not an allowable domain. So how would you know what that is, or what that would result in? So let's think about that. This is a little trickier than I would put on a test, but let's still think about it. So the question is, x squared, if you set this equal to 0, are there any cases where it's equal to 0? Because if it doesn't equal 0, it's not going to be less than 0. So let's see, can we factor that? Well, one way you could plug it into the quadratic formula and see whether if it has any solutions to it. You could also use completing the square. Let's just look at the quadratic formula. We haven't looked at that before, but the solutions would be x is negative b plus or minus the square root of b squared minus 4ac over 2a. So to get a solution here, b squared minus 4ac has to be greater than or equal to 0. If this is less than 0, then you can't get a solution. So what we would do is we would plug in the numbers. So we've got a is 1, b is 1, and c is 2. So you get b squared minus 4a times c, and we'd get -7. So what that means is there are no x-intercepts. Therefore, no solutions. And because this is positive and this is positive, it would turn out this is always greater than 0. So what that ultimately means here is that the domain of this function is all real numbers. Doesn't matter what value of x I put in there, this argument is going to be positive. Okay, let's look at another one here. Let's do f of h of x. So you plug this into here. So you get 1 over x minus 3 squared plus 1 over x minus 3. So again, I haven't simplified it. And any time you have x equal 3, you're going to be dividing by 0. So even though actually this is the domain that applies. So we'd say the domain here would be all real numbers except x cannot equal 3. Again, I'm creating a composite function, but I'm not simplifying it. Okay, let's do the other way around. H of f of x. So there we plug that into here. So you get x squared plus x. That would go in for x here minus 3. Now in this case, you can get x-intercepts. You know, this x squared plus x minus 3 cannot equal 0, because if it does, then this expression divides by 0. And again, this is not an easy factorable expression. You could use the quadratic equation or completing the square to find the solutions where this would go to 0, and that would be where the domain does not exist. So the domain here would be all real numbers except where this is equal to 0. Let me just show you how you do this. If you use completing the square, so you take the coefficient here, 1, divide by 2, square it, equals that. So you get 1/4, 1/2 squared. So you'd add 1/4 here. You'd subtract 1/4. You'd make this into a complete square, x plus 1/2 squared. Over here we'd have negative 3 minus 3/4. So that'd be 12/4. Negative 12/4 minus 1/4, that'd be negative 13/4. So you take the square root. Okay, so then what we do is we take the square root of both sides. And then we subtract 1/2. And so we get an answer. There's two solutions. Negative 1/2 plus or minus the square root of 13/4. So if we go back to our original expression, those are the values of x which cause this to go to 0. So it would be all real numbers except these two. Okay, let's look at another case here. Let's say we have h of g of x. So we're going to take g of x and plug it into here. So we'd have 1 over, instead of x minus 3, we'd have the square root of x plus 2 minus 3. So what we have is, are there any circumstances where the denominator goes to 0? So you'd have x plus, square root of x plus 2 minus 3 equals 0. This is the case where this function would not exist. So if you add 3 to both sides, you get that. And then we'd square it. So we would get x plus 2 is equal to 9. Subtract 2 from both sides, you get x equals 7. So if you plug a 7 in here, you'd have 7 plus 2, which is 9. Square root of 9 is 3. 3 minus 3 is 0. Now, yeah, so that's pretty much it. So in the case of this composite function, it would be all real numbers except x equals 7. But again, you take the composite function without any simplification and then apply the requirements that the square roots have to be greater than 0. The argument of the square roots has to be greater than or equal to 0. That the denominator of a reciprocal function cannot go to 0. Let's do the other composite function. I think that'll be enough for right now. Okay, so we said that x cannot equal 7. We also have the requirement that the argument of the square root has to be positive. So x plus 2 has to be greater than or equal to 0. And so x has to be greater than or equal to negative 2. So the way we would do this, take both of these into consideration, is that we would start at negative 2. We can include negative 2. And then we would go all numbers until we get to 7, but not including 7. And then we would go from 7 to positive infinity. So that would be the domain. If x is less than negative 2, then you get a negative square root of a negative number. So it has to be greater than negative 2, but you can't have it equal to 7 as well, because that would cause this part, the reciprocal function, to be divided by 0. So they can get a little complicated. Hopefully I will not give you one that's too difficult.